Okay, so I'll start with the intro. So thanks, Gail, for coming. Gail is a PhD student at Technion, working with Eran Yahav and Yoav Goldberg, and her research focuses on the application of formal language theory to deep learning techniques, and particularly those used in NLP. And today she'll talk about her new work, Thinking Like Transformer. And if there are any questions during the talk, feel free to interrupt or ask either in the chat or directly. And if you write, I'll just direct you to Gail to answer. Yeah, so let's go.
Okay, so the first thing I should do is try to share my screen. Which we know works, but always has to happen one time. And let's. So, can everyone see me? Can everyone see my screen?
Yeah.
Great. Okay, so hi everyone. Like I just said, I'm here to talk about transformers and try to understand the formal languages and transformers. I'm going to try and motivate the fact that transformers are very popular, though probably most people in the audience know this. The fact that applying formal languages to understand things is fun and cool, and then the question of how we even get to doing that with transformers. So the first thing is, of course, transformers are big and fun and popular. They're highly parallelizable, so we can train them pretty fast on a lot of data. They're very powerful. Pretty much every popular, maybe I shouldn't say every, but a lot of popular machine learning models for text processing are transformer-based now. They're powerful at everything, really taking over NLP. And the thing is that we don't really know how they're working or how they're doing what they do. So it's not that we're not asking these questions, and we are figuring out all kinds of things. So, you know, there's this one work by Unital saying that there are universal approximators of constant length sequence-to-sequence functions, which is cool. That tells us that they're very powerful. On the other hand, there's a different work that says, okay, but when you use hard attention, then actually there's hard attention and unbounded length sequences, then actually there's very simple tasks that you can't compute, such as parity, or even if you don't use hard attention, just your ability to model these languages reduces as the input length increases. There's a discussion on their ability to recognize formal languages, where Batamitra et al. Recognize that for certain regular languages, even though transformers are supposedly, very powerful, there are certain regular languages that they can't recognize, which is also interesting, and they try to discuss what kind of regular languages are they, why. There's also more recent works on Turing completeness of attention. I think at least one of them is using the encoder and decoder model for this proof. I'm here more to talk about the encoder model specifically. So we've got all these kinds of discussions of power. Technically they can do anything if they have enough precision and they have a bounded length. On the other hand, in certain senses, if you restrict them in certain ways, they can't. But these things sort of tell us the power, but they don't give us the intuition of how they would solve a certain task. So let's say instead of saying that we couldn't solve parity, we would say that they could. How? What's the construction? What's it doing? So what we really need is a model. And if we look at RNNs, it's not that far-fetched to want a model, right? So RNNs do have a computational model, and it's finite state machines. At this point, I have to say I'm very open to questions, interruptions, anything. I don't have the Dory thing, but I assume you would tell me. So I'm going to assume that everyone is very familiar with the fact that recurrent neural networks are quite similar to finite state machines in their behavior, in the sense that they both process an input token one at a time, updating a single state with every new token. until finally a final state is reached, and then it's decided, the classification of the entire sequence is decided based on that final state. And with this kind of parallel, when we understand that an RNN is kind of like a finite state machine, then we get all kinds of great things from it. So we get extraction. We say, okay, RNNs are kind of like finite state machines. Let's convert a trained RNN to a finite state machine. We get the analysis of expressive power. Okay, so it's like a finite state machine. Does it have augmentations? Is it like maybe a finite state machine with something more? Is it like a specific type of finite state machine? And so on. And so we get, that second order RNNs are exactly equivalent to weighted finite automata. We get that LSTMs are actually finite state machines augmented with a counter. We get that GRUs are more similar to DFAs if we assume saturated activations. Things you don't have to understand, just an intuition that we get a lot of value from knowing that an RNN is like a finite state machine. We even get inspiration. So we know that if a finite state machine gets increased power by being given a stack, then maybe an RNN will get increased power from being given a stack. And all these wonderful things we have, and we don't have them for transformers. So now I'm going to give a slide. The whole point of the slide is just a list of works, screenshot, come back to the video when you're done, whatever. It's just here to know it's not a complete list. It's a list for anyone who's interested in the stuff that I just talked about. And now we come to transformers, and we only focus on the Transformer-Encoder, which is half of the entire transformer model, because there is a limit to how much we can deal with, at least at a time. So we know that recurrent neural networks are like finite state machines, or at least we pretend we do for the sake of this talk. What is a Transformer-Encoder like? Does anyone in the Zoom want to volunteer ideas on what a Transformer-Encoder is like, or I'll continue alone? As you please. I'll continue. So we don't really know what a Transformer-Encoder is like. Let's start taking a look at how it works. So what's a Transformer-Encoder? It's a little model, a neural model that does the following. It receives a bunch of tokens, a bunch of input tokens, all at once, doesn't really care about the order between them, and processes them all in parallel in a transformer layer. And then it outputs a new set of embeddings from these tokens, and then it repeats this process some fixed number of times, going through each one of its layers, each of them doing a slightly different computation because they have different weights. Okay, what does that mean? The first thing it does is it gets a bunch of input tokens. Let's say we give it the sequence, I like dogs. Next, we encode this bunch of tokens into a bunch of vectors, which we will give the transformer. At the top, we're going to encode each one of the words. The transformer needs to know which tokens it received. And at the bottom, in the lighter pink, we also have to encode the position of each word. Because as I just mentioned, the transformer doesn't actually care about the relative positions of the inputs it gets. It doesn't know anything about that. We have to tell it the position of each word. We combine these and we get the initial encoding of our input sequence, which tells us very little, but it's what we start from. And then we begin to feed this encoding into the Transformer-Encoder layers. So a layer takes all n of the embeddings, does something to them, outputs n new embeddings. This is repeated for each of the layers, and finally we get the output of the entire transformer. Is this thing anything like a finite state machine? By which I mean, is it processing input tokens one at a time? The answer is, of course, no. This thing does not have states. What does it have? Anyone have a guess how they would describe this, pretending they don't know what RASP is? Okay, what it does have, not a sense of reading an input token one by one, so it's not stateful, but there is a sense that information is being propagated and aggregated, right? So we begin with some very basic information, just for the word embedding and the positional embedding. Something happens, mixing it together, creating further information, hopefully more detailed. And this is repeated for a certain amount of times, which feels a little bit like a finite snippet of code, right? We've got essentially variables. Each new variable is created from the previous variables. And the layers are kind of like the operations that are applied to these variables. So kind of, we could say that it could be described by a programming language, that a given transformer is a short snippet of code in this programming language. And so we will try to abstract the transformer as a programming language. And this programming language is called RASP, Restricted Access Sequence Processing. And with RASP, what we say is, okay, a transformer-encoder is a sequence-to-sequence function. It takes a sequence of a certain length and returns a sequence of the same length. It can handle any length, provided we know to tell it the positions, and will give an output with the same length. Each of its internal layers applies some kind of operation to this sequence, creating new variables. And our program is going to describe what the initial sequences are, so that's our word embedding and our position embedding, and what kind of operations our layers can do to them. So let's begin with the input sequences, the very first things that we begin with. If we look at RASP, the very first thing we have is the word embedding and the position embedding. So the very first thing that RASP should give us when we start it is simply the tokens and the indices. And just for fun, let's try and make it feel real. Let's really look at RASP as we do this. So so the first thing I'm going to do is I'm going to have if our input, so here it was I like dogs, let's change it to I like dogs. Okay, and let's look at our tokens and our indices. What it does is it takes our input sequence, I like dogs, and it says, okay, your tokens are I like and dogs, because we're going to stay at an abstract level. We're not going to actually get into the actual embeddings. We're trying to abstract what the transformer is doing. And the indices gives us the integers 0, 1, and 2, the positions of I like and dogs. And now let's continue. So I've got my tokens and my indices. They are simple functions that tell me this is what we will do to a certain input. I can turn the examples off if it starts annoying me. And now we have these initial embeddings. Obviously, that's not all that a transformer tells us. It's doing something. So what kind of things is it doing? So in order to understand what kind of things it's doing, we're going to have to actually go into the Transformer-Encoder layer and poke around and see what's in there. So here it is, the Transformer-Encoder layer. A lot of stuff happening here. Let's focus on things one at a time. The first thing we'll focus on, simply because it's easiest, is the feed-forward sublayer. All we really need to know about this is that it is an element-wise application of a feed-forward network to each of the embeddings that is given. So X1, X2, X3, each one independently is manipulated by the feed-forward sublayer, and something new is given. Not exactly X1, X2, X3, because as you can see in the layout of this layer, some other stuff is done to them first, but you get the idea, I hope. Okay, and this is a 2-layer feed-forward sublayer. And from the results of Honig et al. From 1989, we know that multi-layer feed-forward networks are universal approximators. We take that, we know that it's not really saying we can do literally anything, but we take that and we run wild and we say we can do any element-wise operation. If we've given too many, we'll come back and fix that later. For now, RASP, you're free. Up to what we've defined in the language. So now we allow ourselves to do any kind of feed-forward, any kind of element-wise operation on our tokens. So for example, if we look at our example here, I can do indices plus 1. And it will tell me on your input, I like dogs, instead of 0, 1, 2, it's going to be 1, 2, 3. I can do indices times indices just to see what happens. And I get the square, so 0, 1, and 4. I can do is the tokens equal to the word I. And we get that that's true for the first word and the rest are not the word I. So we get this kind of simple element-wise operations that we can apply to each of the values on our input sequence or in the indices of the tokens. And then we can build on that, right? So, I don't know, tokens I, let's do an indicator of that. So now it's 1, 0, 0, and I can multiply that, or I can add that to the indices just for funsies. So I'm just doing all kinds of element-wise operations. All right. That makes sense to everyone? I hope so.
Like, how do you do it in practice?
What do you mean?
Like, I understand that you write a command and something happened, but like, how is it computed?
Underlying, how is this implemented?
Yeah.
Basically, these are a bunch of classes, I guess. Like we've got a compiler here, and what it's basically doing is it's creating a bunch of functions. So indices in practice, the underlying object that we have is a function that takes a sequence and returns a sequence of the same length. And the specific function is I'm going to return just the indices of that input sequence. And then each one of my operations is actually just a function composition. So indices plus indices creates a new function.
So these are just functions that you build for like this kind of, or like operation that you build for?
What's that?
Like, so these are just functions that you build to operate on the indices?
On the indices, on the tokens, on everything. These functions, you can think of them as sort of representing small transformers. So they're sequence-to-sequence functions. And all of the ways that I can combine them are going to be effectively the ways that I can manipulate information in a transformer. So for example, if in a transformer I can do element-wise manipulations with the feed-forward networks, then I'm allowing myself to combine these functions in an element-wise way.
Okay, I see. So currently it's only the token by token, right? So like the same token with the same token, like a transformation of a token with itself.
What do you mean?
So like currently the operation that you did does not involve, for example, a combination of the first and second token. It's only like a token and something in the same location, for example, the same index.
Yes. Currently it's element-wise. Each position only considers itself. We've only discussed the element-wise operations. What did I want to say? These examples, because these are functions, then just for convenience, because otherwise the compiler would just, the REPL would just constantly be saying, oh, you've made another function. Then it's giving examples. So I've told it that my example should be always tell me what happens on I like dogs, but these are just functions. So if I say that A is indices plus indices, what I've actually made is a function. I can apply the function to a different input. Right now I'm giving hello as a word, not as a sequence of words. So it's going to treat it as different tokens. So we've got effectively indices times 2 for a sequence of length 5, we get 0, 2, 4, 6, 8. I can change my example. And then, shouldn't have done that. And then I can also evaluate the function again. It's just giving me examples of what the function is so that I can follow and understand what the function is. Does that answer the question, I hope? Excellent. So these are called SOPs, sequence operators. They're functions that take a sequence of any length and convert it into a new sequence of the same length.
Could I ask you, ask a quick question? Because I'm not sure I understand what we're aiming for here. Is this like something where we try to understand how transformers work?
Yes.
So basically, this language is meant to be kind of a
thought experiment. You can
a
say
model for what transformers can and cannot do.
yes. So the model will probably need refinement over time, because for now we're just saying, oh, pretty much any element-wise operation, haven't put too much thought in it, and the feed-forward sublayer can't really do anything. But so you have to be, as a RASP programmer, you have to sort of be reasonable about whether you're doing things that you think the underlying operations really could replicate. But it gives you a framework for trying to sort of reason around how a transformer would approach something. So for now, it might seem very simple because we're only doing the feed-forward behaviors, but maybe we're going to want to do something more complicated, for which we're going to have to, kind of gather all kinds of information, and we'll have to think, where will we store it? What makes sense? And then RASP starts giving us the tools for thinking, oh, maybe we should be storing information in the beginning of sequence token. Maybe we should be storing information in the token before the token we're in. So sort of giving us ideas of how a transformer would structure its computations.
But basically, we are talking about a trained transformer. Because, I mean, once the transformer is trained, it represents some kind of function, and each layer represents some kind of function.
Yes.
And then you can argue, okay, each of these functions can be mapped to one of your functions in RASP, right?
Yeah.
But that does not mean that RASP could be created in a similar training process. So you are kind of starting with a trained transformer, right?
Yes, indeed. So in the same way that we don't train automata, we don't train RASP, we simply use RASP to kind of try and understand how is a solution being encoded in the transformer.
Okay, thanks. I think I get it a little bit better now.
Okay, all right. I hope so. Entirely a thought experiment, practical applications to come, I hope, or even simply better understanding which someone will use to go and do something cool. We stay on the understanding level. Okay, so we've got our feed-forward operations. How far can I get with feed-forward operations? Have I got everything I need to do whatever a transformer does at this point? That's right, Johan is shaking his head correctly, because I could not possibly get very far only doing element-wise operations. I couldn't even tell you at my final token if the sequence began with A, which I'm pretty sure a transformer can do. So we've got to do a little bit more than this. Let's go look at the Transformer-Encoder Laye. What else can it do? So if we look, in fact, everything in the Transformer-Encoder Laye is an element-wise operation, except for the multi-head attention. So whatever's going in there, we really need that. So let's go into that. Now let's understand what multi-head attention is. And because multi-head attention is basically just a bunch of single head attentions, let's begin with single head attention. So what's single head attention? We get a series of embeddings of length, 3. For the sake of this example and every repetition, so we have a nice fixed word, 3 embeddings, but it changes. N. We get N embeddings. Now what do we do with them? We convert them. I'm just giving you like a dry run, what attention does, no intuition. This is what it does. These are the wires. We'll think about what that means in a moment. The first thing it does is it applies a linear transformation to 2 linear transformations to each of these vectors. One is Q and one is K, creating a bunch of queries and a bunch of keys. The next thing it does, for every query, it computes the scalar product of that query with every one of the keys, creating a vector of length n. So for each query, a number of scores that is equal to the number of embeddings that have been received. It then normalizes these scores because that helps with training. It then softmaxes these scores, which creates a distribution as opposed to a bunch of scores. And then it does a further operation. It multiplies every single one of the input embeddings with a third linear transformation V, creating a series of values vectors. And then it computes the weighted average of these value vectors according to the weights that it just computed for this first query. And then we get the first output vector, which is just a weighting of the value vectors. You could also think of these as candidate output vectors, and we're just sort of choosing how to mix them together into the output at the first position. We then do this for the second position. We compute the scores for the second query, ultimately computing the weights for the second query, doing a weighted average of the same value vectors, but this time according to different weights, creating the output at the second position, and then at third position, and so on. And this is how a single attention head creates a bunch of output vectors from a bunch of input vectors. You'll notice there has been mixing going on here, mixing of the candidate vectors. Multi-headed self-attention is simply the concatenation of multiple single-head self-attentions. So what does that mean? We take our input embeddings, we split them. It doesn't have to be equal, but there would be so many parameters if it wasn't. We split them into H, that's the only parameter we care about, some H set of equal length vectors. So we begin with dx, we split it just by position into H vectors of length dx over H. And we send these groups of n vectors, these n smaller vectors, into each one of H attention heads. We get H sets of n output vectors. We concatenate them back together. We get the output of H attention heads. Does that bit make sense? Split, apply H times, stick back together. Okay, so the multi-headed self-attention isn't interesting in itself. It's not adding some kind of unique power. It's just sort of letting us do lots of operations in a single attention, in a single encoder layer, as opposed to, you know, each layer doing only one self-attention, which will take us a bunch of layers to get there. For that reason, I'm not going to worry too much about multi-headed attention in this abstraction. We're just going to think, how would we represent a single head? So let's look at the single head. What's really going on? Let's try and think of it in this way. The first half of the head operation is this scoring. Every output position selects the input position of the candidates, which it will use to create its outputs. So it's sort of deciding what is called attention, who uses who to create the new output. And so we abstract this into a selector, a select operation. What is this function, the underlying function of selection? It takes two vectors. One vector represents, I'm abstracting here highly because we're losing the fact that it's scalar product. We're just thinking it's making some kind of pairwise decision. Let's abstract that to the highest level. So we'll have some kind of representation of the query vectors, some kind of representation of the keys. So, you know, queries are who are coming and saying, this is who I want to gather into my output. Keys are coming and saying, this is the information I can contribute to an output. So if a query and key match according to some kind of comparison that we choose, then that query will go and select that value to put in its output. And this is what it looks like. So vector representing keys in light green, vector representing queries in dark green, comparison between them, equality in this particular case. What do we create? A matrix of who looks at who, where, top is keys, side is queries, who looks at who, we decided on equality. So the first position is going to go and seek every place that's been described with a 0. So it's going to seek and aggregate values from the last 2 positions. The second position has in fact chosen no one. And the third position is going to choose the first position to create its new value. It doesn't have to be equality. So I could also do it with greater or equals, which would create a slightly different attention pattern shown here in the corner. And that's because we're doing an abstraction with RASP. We want life to be easier, not harder. How this would actually map to a scalar product at the low level actual transformer is not our problem right now, but definitely something that we can discuss if anyone is worried about whether that's a fair decision. So we somehow decide who's going to look at who, and now we're going to aggregate. So what does that mean? We're going to create some kind of value or take some kind of value and do an average over who we've selected. So the aggregate operation looks like taking a selector, the attention matrix that we've just created, taking the values and doing the weighted average. So first, with our selector, we filter for each position the values that we're going to average, the values that we're going to take. So in the first row, we took only the last 2 values. In the middle row, we took no values. In the third row, we took the first value. We average them, and we get our output vector. There is one technicality, part of the abstraction of RASP. We allow you to select no values, as we did in the middle row. In this case, when we average, we use some kind of default value, in this case, 0. So that's what aggregation looks like. Any questions on selection and aggregation? Let's hope not. Okay. So for example, so another point to make about the aggregation is it's technically averaging, but because RASP wants to abstract and make life easier, and it's symbolic, then we don't have to average. We allow ourselves to not average if a single value is chosen. And that allows me to do, for example, the operation here, where on the left, I've created a selector that only picks a single input position for each output position. So my averaging will be only on one value. And for this case, I allow myself to aggregate on characters as opposed to numbers, meaning things that can't actually be averaged, because I've only chosen one, so I don't worry about it. What would this mean in the underlying representation? You have, the vector representing C. It gets averaged with no one else, so it remains the vector representing C. And we, as the RASP programmer, don't have to worry about this conversion to a vector in the back. That's not our problem. Maybe this would be a good time to look at that. So for example, I can select every position where the indices are equal to each other. Let's change the... Okay, so here, every position on the left, the output position, on the top, the input position, if I remember correctly, has chosen to look at those that are the same as itself. I can also choose to look at those that come before me. So in this case, I've created a sort of causal attention. The final output of whatever I aggregate with this selector will be an average of all the inputs, and so on. So I can create, for example, a selector that looks just at the same position. I can also compute the reversed indices by taking the length minus the indices minus 1. That's just an element-wise operation. And then I can compute the flip selector. So I take every index and I seek the reversed index, the opposite index. And in this way, I can reverse an input sequence. So I take my flipping selector and I aggregate the tokens with it. And in this way, I reverse an input sequence. Does anyone have questions on that? Want to see more examples, sort of think about that, play with that?
I have kind of a more general question. How do you prove that this is actually what the capabilities of transformer block can actually do?
So it's
like it makes sense, but like how can you prove such a thing?
I don't know how you can prove it.
Okay.
So maybe one by one specific operations you can prove. So I can prove, for example, equality. If I've proven that the things that I'm putting into the selector I can compute, then equality I can probably prove, because that's very easy to do with a scalar embedding, right? I can just that's what it looks for. I just make Q and K the same, both representing this value, and I get equality. For less than equals, so for selecting previous index, I need a slightly smarter embedding that has every query select all keys of things that come before it. So for example, I could have my keys be one-hot embeddings of the position, and my queries be sort of multi-hot embeddings that select all the positions that they're willing to take. That's not the most efficient embedding for causal attention, but it's an option. So every time you really want to take a RASP program and say, can I really do this in a transformer? You still ultimately have to handcraft the weights, but it does give you a framework where you can think on a high level and later come to the specific weights. Yes.
I am also still struggling with this idea of mapping this kind of discrete approach to computation with the more continuous approach that you find in the transformer. Because, I mean, from a theoretical point of view, for example, with the simple situation where you just look at the feed-forward network, okay, we can prove that you can approximate any function if you have enough neurons, right? But that's the caveat here. You need a lot of neurons for some functions. But this is still only true if we assume it's already trained, right? We do not know what kind of function you can actually train with gradient descent, because that's a very strict limitation, actually. I mean, as long as you can just invent any weight you want with any number of neurons, you can approximate any function. But that's not what you can do with anything we have invented yet for training, right? So in a way, you probably can do more with RASP than you can do with a transformer if you're also interested in the training. Do we agree on this?
Yes.
Okay.
It's also possible that there are things that you can do with a transformer that would be extremely difficult in RASP, because a transformer, just by the nature of the transformer, can handle these huge amounts of data, whereas in RASP, some poor human would have to sit and write all of the rules for what transformers are trying to do with natural language. So it kind of goes both ways. The intersection isn't exact, and this is true also for the connection between RNNs and automata. So I'm not claiming that RASP is an exact representation of transformers. There is no exact parallel between the two in either direction. It's more that it's just a very close abstraction that for people who are asking things like, how does the soft reasoning paper work by Clark et al., the one that does the logical reasoning over, what is it? Harry is a wizard. Wizards can do magic. Can Harry do magic? Kind of stuff like that. So the fact that a transformer can do that sort of raises questions of how, where is it computing this information? What's it doing? And it's things like RASP that allow us to take a step back from the weights and the exact things that are happening and sort of look at the more high level of what's the information flow of a transformer? Where where would I, like, if ignoring the details of what I can exactly compute and how difficult this would be, where does it make sense to store information? What kind of partial computations is it useful for me to do at the third layer in order to compute this sort of logical reasoning thing? It's mostly about the information flow. Does that explain the goal?
Yeah, I think I get the feeling about that. You want to use it as a tool to think in a different way about what might be going on. Is that what it is?
Yes.
Okay.
The title of the paper is Thinking Like Transformers. So it's there to guide us with respect to the information flow. It's not here to claim to be an exact equivalent of transformers, nor a superset, nor a subset with respect to the languages that it can represent.
Okay, and do you think it is possible to actually use this then to prove anything?
So if you make a proof based on the information flow, and so you would say, you know, it is simply not possible through the channels that RASP gives me to move this data and gather it correctly into this position, then you have a proof on transformers. But generally speaking, you know, a positive result in RASP still has to be shown in concrete ways in transformers. So the relation isn't tight enough to simply prove things easily. No.
Okay, thanks.
Hope not to disappoint anyone too much here. Okay, so for those that want to think like transformers, let's continue. So,
by the way, technically we have about 13, 15 more minutes. We can stay a bit longer, but just so you have the time in mind.
15 as in 1-5?
Yeah.
Okay.
But we can also stay longer if you want.
I can stay as long as everyone wants. If anyone has questions, they should say them. If not, then I will continue.
Sounds good.
Okay, so simply interrupt me with questions. Okay. So we just gave this example of reversing in RASP. So I create this sort of flipping selector, which will allow me to reverse because I can do these pairwise decisions. What would happen, by the way, if my selectors were not making pairwise decisions? The answer is that then I would be doing effectively arbitrary computations, right? I could, like, not arbitrary, but if I didn't restrict the select decisions, then I could sneakily put their Turing complete power if I wanted, and simply point the transformer to the correct answer to grab from there, things like that. So they are pairwise to reflect the information flow constraints of the transformer, completing the reverse decision. By the way, is there anything suspicious in the example that I gave here of reversing an input sequence? The answer is there is, and that's length, which is actually not part of the input to a transformer. And the reason I can use it is that we can compute it with a transformer, and hopefully we'll get to that. So that's all the parts of RASP. We've got the initial sequences, which we describe as indices and tokens. We've got the feed-forward sublayers, which allow us all kinds of element-wise operations. We've got the attention heads, which are represented by the pairwise select and aggregate. And there's technically also other things. So we didn't discuss them, but there's the residual connections in a transformer, which are also what encourages this idea of, like, I create a variable somewhere in the code and it's still available later. It wasn't hidden by a new computation, it's being brought forward. And there's a layer norms, which is sort of something that is used for regularizing and training. It's helpful. For some reason, it's element-wise, and I'm not entirely sure what it does or how it affects things, so it's an open question. It hasn't been taken into account in transformers, in RASP. It isn't transformers. And that kind of gives you all of RASP. Let's do another small example of computing length. Does anyone have a clue how to compute length? No? Okay. So how I would compute length is with the use of these averages, and I'll give you a small clue. I'm going to create an indicator for indices being 0. So my entire vector is just going to put a 1 at the very beginning. And I'm also going to use a full selector that loads into every token something from everything. Does anyone have an idea where I'm going with this in our tiny Zoom chat? Let's try and look what happens if I aggregate a full sequence with 1 from only one position. What I'm actually going to get is 1 divided by the entire length of the sequence. So 1 over the length. And then all I have to do in order to compute the length itself is first aggregate this to get 1 over the length, and then compute the inverse in order to get the length. So that's why length is fine and allowed in RASP. Okay, so overall we've got indices and tokens, select, aggregate pairs, and feed-forward operations. How does this relate to a transformer? We do want still on a high level to relate to a transformer. So we've got this idea that the operations are part of transformer layers. Moreover, we know that indices and tokens are part of the initial embedding, so they create no layers. The select aggregate pairs have to come to attention heads. So then, because attention is at the beginning of the transformer layer, they start new layers. Every select aggregate pair creates a new layer after the last of the values that it's using. And the feed-forward operations, they happen at the end of layers. And we can tack them on. We're just going to go ahead and assume the arbitrary power of the feed-forward layers. So, for example, for reverse, the first thing we do is we do this full selection, which allows us to compute the inverse of the length in its aggregate, and then we compute the inverse to get the length itself. We do an element-wise operation to get the indices in reverse order, so that's length minus the indices. Having obtained that value, we can create a selector based on it and the original indices to create the flip selector. This opens a new layer. And then a final aggregation of the tokens with this selector creates the reversed input sequence. And now, as I've been asked throughout the talk, has this got anything to do with reality? Are we predicting the right number of layers? Are we predicting relevant selector patterns? So we don't have proofs, but empirically, for very small examples, there is a relation. So if we look at reverse, RASP says, first, in one layer, using uniform attention, you have to compute the length. Then, and only then, in the next layer, you can create the flip selector, which will reverse your input sequence. So you need 2 layers. Is this going to happen in reality? So let's go and take a transformer and train it on reverse and see what happens. First of all, we see that indeed 2 layers is enough. So when we train the 2-layer transformer as requested by RASP, and we're not telling it how to do things, we're just training it on reverse, then it manages and reaches a very high accuracy very quickly. Moreover, if we do 1 layer, which is less than requested by RASP, we actually don't manage to train it on the reverse language. This is for varying input lengths. And that makes sense because in RASP, it tells us first you have to compute length, which will take an attention head itself.
Here, do you also train a decoder, or is it still just an encoder?
Well, just encoders for this whole talk. So
how do you do?
So by reverse, what I actually mean, when you consider the last set of sequences, the last set of embeddings created by the encoder, I apply a further classifier to each one of these embeddings, which converts to a token.
Got it.
And I want the classifier to convert the final embeddings back such that I get a reversed sequence. Okay, so for 2 layers, I manage reverse. For 1 layer, I don't manage reverse. And moreover, if I look at the layers for the 2-layer transformer, then I get what made sense in the RASP program. So the first layer has this kind of uniform attention. It selected everything just as we would have liked in our RASP program. And the second layer made this beautiful reversing pattern. So it's not a proof that transformers can do this, but empirically there is, at least for the very simple programs, some relation, which is nice. A different example is histograms, which I don't think, do we finish at 6?
Yeah.
And should we continue? Should we stop at 6?
We can, maybe let's try to wrap it up until 6, and then we can stay for additional questions on or random thoughts.
So, okay, so we have a non-trivial way to compute in-place histograms. So first of all, on the side, you're seeing an example of what I mean by in-place histograms. For every token, we count how many repetitions of that same token is present in the sequence. We're assuming a beginning of sequence token, which we don't count. So that little section mark counts 0. It's not there. We're not paying attention to it. And so we're computing this in-place histogram. There is a way to compute this in RASP. I'm not going to go into how, but there is. And this is, it takes one attention head in one layer. And what this attention head does is it focuses each position on the positions with the same input tokens. So every token looks at all positions that has the same token as itself. And on the first input token, that's where the beginning of sequence token is. It allows itself to use it for help. On the left, we see the compiled RASP program. So this is the selector pattern that we're creating in order to compute this value, this in-place histogram. On the left, we see a single layer, single head transformer trained on this in-place histogram problem. And both are shown on the same example sequence. And we see visually a strong correlation between the two. So it seems that the transformer has again learned a very similar solution to the one that we also like to encode in RASP. So that's nice. Again, not a proof that every program in RASP will be realizable in a transformer or any kind of direct relation in any direction. But it means that this model is directing us to think like a transformer, which is the point. What other insights do we have? So all the RASP programs don't have any loops, simply because transformers don't have loops. And that kind of holds us back. In fact, it means that there's no RASP program which will have complexity greater than n squared in the input length, because we've got a constant number of operations, and the most complicated operation takes n squared time. So we're limited. And this further motivates the universal transformer, which allows looping based on the input. So the transformer can decide with itself whether it's going to repeat some kind of operation. Another thing that may or may not arise from looking at RASP, I think it does, is this idea that there's no point to multiple feed-forward operations in RASP before we apply an attention, right? We've begun with the words and the tokens, and no amount of element-wise operations is going to create something more intelligent than that, something that carries more information than that. Not until we start mixing things. So we get the idea that there's really no point feed-forward layers before attention layers. And there's this work on the sandwich transformer where they try to sort of reorder the overall self-attention layers, and the self-attention sublayers and the feed-forward sublayers of a transformer, so sort of mixing around. And they really saw that it's better to first have self-attention layers and then feed-forward layers, with some interaction, because the feed-forward layers are ultimately those doing the computations, whereas the self-attention layers are just aggregating things. But definitely that there's very little point to having feed-forward layers at the beginning, which is in line with our results. A proof that RASP can compute sorting, arbitrary sorting, by which I mean a program showing arbitrary sorting in RASP, suggests that at least the information flow constraints of a transformer do allow for use of at least n log n, which is, we know, the minimum needed for sorting of the computational cost that transformers have. So we know that at least we're not completely wasting our time with these n-squared operations. Though I haven't found something that really I know has a lower bound of n-squared to prove that it really uses everything. I'm gonna wrap it up with this. If we want to stick around and talk, we can talk about these talking points or anything that you come up with. That's it. It's on GitHub, and what I showed you is what's online, and you can play with it. Maybe here to try it out. Any questions?
Thanks a lot, Gail.
Hi.